Good morning, everyone. Thank you for joining Mega Asia webinars. I'm Grace from Mega Hong Kong. Today's topic is DC insulation resistance testing, the use of guard terminal. This is a recorded webinar, and you're automatically muted to prevent any background noises. And during the webinar, if you have any questions, please type into question panels, and we will answer your questions during the Q&A session. And you can type a question anytime during the webinar. So without further delay, let's start now. And the presenter today is Nick Rees, who is the application specialist from Dover.
Hello, everyone, and thank you for joining us today. Welcome to Mega's monthly Testing Tactics webinar series. Today's topic is DC insulation resistance testing, effective use of guard terminal. My name is Michael Fleischer, and I'm the digital marketing specialist for Mega. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you'll see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NIDA CTD and one PDH or 0.1 CEU for attending. You will receive this in an email within 2 business days of the webinar. That email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation. They will be answered at the end of the webinar during the Q&A session. Our presenter today is Nick Rees, Application Specialist. Also, to assist with the question and answer session, we will have 2 panelists joining us today. We have Volney Naranjo, Applications Engineer, and Dinesh Chajer, Technical Support Group Manager. All right, let's go ahead and get started. Thanks for joining us today, Nick.
Hey, good morning, good evening, good day to you, wherever you are in the world today. A warm welcome to this webinar on HVDC insulation resistance testing, and of course the effective use of the guard terminal as used on many of Mega's insulation resistance testers. My name's Nick Rees, and I'm part of a team of application specialists based at one of Mega's manufacturing plant sites at Dover in England. So my team is collectively responsible to support our sales teams for current products that have been manufactured in Dover, and our support for these products extends globally. However, if you have a query on any of the Dover products, the first point of contact will be your local sales team, and these email addresses and contact numbers will be shown at the end of this webinar. Okay, the objectives today is we're going to have a bit of a very quick history lesson. I'm not going to bore you too much. Then we're going to talk about HVDC insulation resistance testing and surface leakage. We're going to talk about why we need a guard terminal. We're going to move on to talk about how we overcome surface leakage and the advantage of using a guard terminal. We're going to talk about the challenges and the constraints when designing a guard terminal. And take a look at Mega's high performance guard terminal and why it's so special. Then we're going to have a bit of a question session, and at the end I'm just going to leave you a few pointers just to remember, just to take away with you. That's the points to remember. Okay, so blasting on the history lesson. Here you see 2 very old pieces of paper on the screen. This is what you'll see here is the very first edition of the wiring regulations for the United Kingdom. They were dated May the 11th, 1882. So, you know, this is the first regulations that would come out. And today, what they identified in them 2 pages was risks. They saw that there was a lack of knowledge and poor installation methods. They knew there was an issue with moisture and corrosion. They could see that there was sometimes short circuits and faults to earth. And of course, they had high resistance and bad connections. Today, we're doing more with regard to short circuits and faults to earth, potentially. So as you can see, you know, these were the very old edition, first edition. That edition was 136 years old, and 61 issues and amendments later, we still use these fundamental principles of risk prevention, protection, and testing, and they form the basis of safe use of electrical systems. And since 2008, each amendment has maintained technical alignment with Senelec harmonisation documents. And here you can see a number of different standards in different countries and obviously the international ones. So not only did you see in them first standards identified risk, but they also identified preventative measures to mitigate and control these risks. They talked about testing and probing with electric currents. They talked about the frequency of electrical testing. They talked about the use of special test equipment. Okay, and some of them vocabulary that they've used appears a little bit old-fashioned and somewhat strange to us today, but the meaning and fundamental needs of our current standards, our guidance notes and regulations are based firmly on the words of our predecessors. They are still part of our core today and probably will be well into our future. So that's the history lesson over. I hope that wasn't too uninteresting, but it does give it a little bit of a spin on why we're where we're at today. Okay, so when do we start to use insulation resistance testing? Well, the first consideration would be during manufacture. When a transformer or a cable is manufactured, it would be first energized and tested in the factory, and before it's actually energized for the very first time, they would perform an IR test on that, an insulation resistance test using a HVDC voltage. So when we place an order for our asset and it arrives at our site, or it's going to be replacing in our switch room or something like that, then we would do an initial acceptance test and perform an IR test then also. So once we've installed it into our system, before we actually switch it on during commissioning, we'd also put it through its paces and give it an IR test before putting it into service. So that would be during commissioning. And then, of course, as it said in them regulations and them standards, it talks about the need for routine testing, for regular testing. So we would thoroughly advise periodic testing throughout its working life. Now, if you've had to do some maintenance on the product, maintenance on the asset, you've taken it out of service, you would also perform an IR test before putting it back into service. Make sure everything's been connected up quite properly and everything's hunky-dory. Okay. So another way in which we perform an IR test, another time would be if we've had a prolonged shutdown, maybe in the factory environment where they've been shut down for up to 2 weeks. The whole factory's been, everybody's off except for the maintenance engineers, and there'll be a team of engineers assisting them to get stuff done quickly in that 2-week period. The heating's probably likely to be off, the machines will not be operating, and moisture starts to go into some of the insulation material. Now this is particularly noticeable on motors, so we need to perform an IR test to ensure there's not too much moisture induced into the windings at that point. If there is, we would need to do a retrospective heating to drive out that moisture before we could restore the IR value and put it back into service. So why do we actually do IR testing? Well, first of all, we need to make sure that it meets the standards without breaking down. That could be a standard set by a manufacturer, or it could be something that a utility company, for example, has some defined standards of which they want you to pass. We want to make sure there's been no environmental factors that have damaged the insulation over time. This could be UV, it could be heat, it could be lots of things, and we'll talk a little bit more about that as we go on. We also want to monitor the quality of the insulation over time. There's one thing sure about insulation, it never improves, it always degrades over time. So knowing that, we need to make sure that we can prevent things from happening and we can predict when we need to do some maintenance. And of course, we also need to ensure safety of people operating the products. So when we start to look at testing, we need to have consider a bunch of different things regarding, first of all, would be the product itself, what sort of tests we need to perform on it. So the test equipment that we manufacture can test up to 15 kilovolts. The more voltage that you apply, the better the signal to noise ratio, and the higher the resistance value that can be measured. Okay, so you would utilize a voltage suitable to the product under test, but we'd also be looking at the current of that instrument. What can it output? If it's just 1 milliamp, it's unlikely to charge a cable in any short period. So we would obviously advise, if you're going to test very long cables, then you would obviously go for a much greater short circuit current in the region of 6 milliamps. Now, when we talk about resistance up to 35 teraohm, when an asset is initially put into service, we want to make sure that we can actually measure a value. Now, if we used an instrument that had a value, say, up to 1 teraohm, for example, and it happened that our asset was a good quality asset, and it was capable of an IR value of 7 teraohm, our 1 teraohm instrument would only say greater than 1 teraohm. Now, this greater than is not going to be any use to us when we come to doing some trending. We need to have actual values, finite values that we can compare against. Okay, that's very important. So when we're trending, we need to normalize these values. We need to normalize the way in which we perform the test. We also need to correct for certain environmental issues with regard, for example, temperature. Okay, but we'll talk more about that as we go. So with regard to electrical noise, we may be in a vicinity where there is electrical noise. Now, our instruments combat that in various different ways. So we have a basic filter that is on our system and is always on, no matter what you press. Then we have two other ways of attacking it. Well, it's actually three other ways. The first would be the use of screened leads. This is a very basic method, but it overcomes some of the challenges that we can find in high electrical noise environments. We can then use two types of filtration. We have a basic filter, which is, as I said, always switched on. And then in addition, we can add hardware filter, which was a low pass filter designed to take out frequencies, various frequencies, including 50, 60 hertz mains frequencies and their harmonics, and of course, frequencies much greater than that as well. There's also long duration fluctuations, where, for example, you may have some environmental thing that's changing. It could be the wind changing direction and changing the evaporation of our layer of moisture on our asset. Okay, so things like that can be taken out using what we call averaging filters, and these can be switched on and off during the actual test itself and counteract and smooth the measurement. So why does insulation degrade? Well, first of all, one of the major ones is electrical stress. You know, our assets are often exposed to spikes, overvoltage, transients, and the likes of that. So they're all subjected to things that they're not designed to be, not designed to operate on an ongoing basis. Okay, there's an operational voltage, but they are exposed to voltages much greater than that during its life cycle. And of course, we have mechanical stress. This is particularly relevant when we start to talk about motors. Vibration in motors can damage them very, very quickly. Movement of insulators, there could be a cable that's moving and abrading against something, or there's impact damage as a result of poor handling or something that's happened during transportation. And then we have the environmental effects. We mentioned UV, okay, but we've also got dirt and oil, and sometimes in some factories we've got corrosive vapors. These all can attack our insulation material. Now, of course, most assets don't operate constantly. They often stop and start. They often go on load and offload, and as a result, you have hot and cold cycles that can affect the thermal stress of the insulation material. And then, of course, we've got environmental conditions. We've got moisture to worry about. That can creep into our insulators. The humidity, what it's operating in, and then we have issues with rodents and birds that can damage or leave their deposits on our assets. So, before you start doing your tests, you need to know a little bit about the product that you're actually testing. So, what is the rated voltage of the equipment, or the cable, for example? What you would expect to see as a pass or as a fail for the applied test. So, it's pass-fail criteria, and it was mentioned that can be from a standard. It could also be from an operating procedure from a utility. And then we need to think about test lead selection. Are we going to be exposed to noise? Do we need to use screen leads. Do we also have a surface leakage issue, in which case we could use what we call a Gills kit, which is a guard insulator linkage kit. So we can link all the acids together that have a problem with surface leakage, and we can guard that out. We also need to know how to test safely. So we need to know how to de-energize, how to lock off, to prove dead, and obviously to earth or ground out before we connect our test leads. We then perform our tests, and then we would earth or ground out again before we disconnect our test leads. So operating safely at all times. We also need to know when to use the guard terminal. Okay, so if there's surface leakage, if it's an acid which has a large surface area and is exposed to the atmosphere, it's likely to have some surface leakage, and therefore guard terminal, the use of the guard terminal would come into play. And of course, then we need to make sure that we're operating the same way that the previous test was done. So we need to know how to record, trend, and interpret these results. Okay, let's talk about surface leakage and polarization. Here on the left, we can see an insulator sandwiched between two conductors. There is no electrical stress across the material, it's in a totally de-energized state. The insulator is in equilibrium and is unpolarized. The dipoles, which you can see in the oval shape, are totally random. However, on the right-hand side, once we start to apply a voltage across the insulator tries to overcome its electronic constraints, and it starts to polarize. It attempts to align itself to the two polarities of the negative and positive. And here you can see the dipoles actually aligning towards the negative plate, so we can get the total system in equilibrium. You can also see down the side, you can see surface leakage. So not only does the voltage cause the current to flow through the insulation material, it also causes the current to flow over the insulation material, because there's often contamination on the surface, and this provides electricity with a lovely path to try and escape from. Okay, before going into the different tests that we can perform, it's probably the right time to talk about the types of current that we can see during insulation resistance testing. When a button is pressed to start a test, the high voltage is produced and a current is generated through the insulation material. The current is made up of three elements. Firstly, there is a capacitive or a charging current, which you can see here in red. Now this decays quite quickly as the cable charges or the acid charges. Once it's fully charged, that current will decay to negligible amounts. On top of that, we have an absorption current or polarization current. As the material becomes more and more polarized, as we saw in our earlier example with the dipoles, this current also decays away. But this current takes much more time than the capacitive charging. And then finally, we've got the conduction, or also known as the leakage current, not to be confused with surface leakage current, but nonetheless, it's also called leakage current. Now, the instrument that we use, or instruments that are used, IR testers, they see the total current. They can't differentiate between the different types of current. So they see the total current, and hence we need to perform our measurements and take their measurements at a time when the capacitive and the absorption currents have decayed away. The capacitive current starts quite high, but it drops away quickly as the device under test charges, in pretty much the same way as a capacitor. The absorption or polarization current starts high, but decays over a longer period of time as the molecules of the insulation of the device under test line up to oppose the flow of current. This polarization can take several minutes or even 10 or 20 minutes to occur, depending on the acid under consideration. Now, the conduction or leakage current normally begins at low levels and settles to a constant value. And this is the current that travels through the insulation and flows along the surface of the insulator once all the other transient currents have decayed. We see this as one current, and that's what we measure with an ammeter within the instrument. And using Ohm's law, we can represent this as a resistance value. Okay, let's move on to the types of tests. There's a very basic test, which is what we call a spot test. It's a manual test. You simply press the button. The instrument outputs a high voltage. The acid under test is charged, and you can either lock it on or continue to keep it pressed until as long as you want to go. Once you think that you've got a stable reading, you can stop the test there and save the value. Okay, so it's a quick no-go test. It's quick to perform, shouldn't be undervalued. However, it gives you a very limited view of an insulation material's condition. Then we can move into some of the automatic tests. On most HV diagnostic DC testers today, these are the types of insulation tests that can be performed. They're all automatic. We have an insulation resistance test, which is very similar to the spot test, but is actually a time test. So the instrument will switch itself off after a duration. The duration is set by yourselves. We have a dielectric absorption ratio test, which looks at the absorption of the insulator. This is a very quick test, lasting just 1 minute. Then we have a polarization index test that takes a longer duration, can be 10 minutes as a minimum, but it can also be much longer than that if you have a long capacitive load that you need to charge. We also have a dielectric discharge test, which works in opposite to the other tests. The other test, we're applying a voltage, you want to take in a measurement. The dielectric discharge test, we have charged the insulator under test, and then we remove the HV, and we allow it to discharge. And we can get a value that can help us to understand the quality of the insulation using the DD test. We also have a step voltage test, which we apply the voltage in steps, as its name suggests. And we also have a ramp test that applies the voltage in a ramp format. So taking the spot test, it's very simple, as I mentioned earlier. You select the voltage, you press the button for a short time, could be 60 seconds, to allow for the charging of the capacitance. Once the capacitance has decayed away, you should see the current start to stabilize, and therefore you get a stable IR value. At that point, we can simply stop the test manually, record and save the result, including temperature and humidity. Again, there are variants that can change over time, so it's obviously best to record the actual conditions at the time of test. And we need to know the pass-fail criteria. So if we have a known value as our pass-fail criteria, we can quickly see if the acid is greater than that. So if for example, it's a 1 teraohm test criteria, and we've got 2 teraohm, we can quickly say that acid's passed. Okay, let's take a look at trending. Let's say we have an insulation resistor of, say, 700 megohms for a cable. This is quite acceptable. Now, if this test had been performed over a period of months or years, as we see here, it started with initial result of 5,000 megohms or 5 teraohms, and each subsequent test, the value has fallen. The latest reading being 700 megohms. So we can see that it's in decline. And this we should have, if it had gone at the rate that it did in the last 5 years, this acid would have failed by now. Okay, so trending of results and accumulation of data is a cornerstone of any maintenance regime. Whether it's a basic planned maintenance or predictive maintenance, the data that we get here is important. So using just one result, the 700 megohm looks quite good and is a pass for this acid. But when trended over the last few years, it's not so good. Okay, although there's been a deceleration in the insulation resistance degradation in the last 2 years, it should have failed already. This deceleration has actually been a chance for the reality for the asset owner to actually get his act together and start to think of replacing this asset very quickly. Okay, the time test is simply an extension of the spot test, but instead of just setting the voltage, you actually set the duration of the test. So you start the test and it will stop automatically, the instrument will stop automatically. You're able to record the temperature and humidity, as we mentioned earlier, And this method is much more sensible when it comes to doing trending, because you can use the same duration on the same asset each time you perform that test. So rather than doing one test at, say, 1 minute and another test at 2 minutes and having a variation as a result of humidity or temperature variation during that time, you're actually normalizing the values and you're able to trend more consistently. Then we can get into some of the more diagnostic tests. This one is the dielectric absorption ratio test, or DAR as it's often known. This compares the readings of an IR value at 30 seconds and again at 60 seconds. And this is when the insulation material is starting to absorb some energy and storing it within its structure. So here we can see when we perform the DAR test, we take two values. We take an IR value at T1, which is at 30 seconds, and an IR value at T2, which is at 60 seconds. In some countries, especially in Eastern Europe, they actually use T1 as 15 seconds, so there's a little bit of a variation there. However, in most places it's 60 seconds and 30 seconds, and the ratio is simply calculated by dividing the IR value at 60 seconds by the IR value at 30 seconds. And from this, we get a value, we get a ratio. And as you can see, we're looking for values in excess of 1.6, would give us an indication that our insulator is excellent. 1.4 to 1.6, we would regard this as good. But if it gets below about 1.4 down to 1, we could say, well, this is questionable. We need to look at other factors. Maybe we need to perform more tests. If it's below 1, we've got a dangerous asset that could fail at any moment. Okay, moving on. The polarization index test. Usually used on large equipment, for example, long cables. It's also very useful in a motor, electric motor. They benefit from a PI test. It's a good way of indicating if there's moisture in the windings. So, but in general, this test is, with many standards, it says a 1 minute and a 10-minute interval, but this duration can be extended depending on the capacitance of the insulation and the length of the insulation. So we can increase the T2 up to whatever we want. But we're really looking for stability in our values. So again, the way in which this is calculated, you've got T1 at 1 minute, T2 at 10 minutes is generally the way which is measured, and the ratio is calculated as the IR value at 10 minutes divided by the IR value at 1 minute, and this index provides us again with more additional information on the insulation material's condition. It can also indicate motor winding contamination from moisture. And with this time, again, we're still looking for a value, a higher value. A higher value indicates a better insulator, a lower value, a questionable or dangerous insulator. So above 4, we regard this as an excellent polarization index. It's below 1, it's dangerous and could fail at any moment. Just as an aside, it might be worth noting that, when you perform a PI test, because you've actually gone through a 30-second and a 60-second interval, the DAR value is provided as part of this PI test as well. So that's actually a good way to actually kill two birds with one stone. You get two tests for the price of one. Okay, the dielectric discharge test. This test differs from other time tests as it does not measure the currents during the it does not measure the currents during the charge cycle. It measures them on the discharge cycle. Okay, so it was designed by EDF in France because it can reveal the condition of insulation system as opposed to an individual insulation material. So if we have an insulation system that has multiple layers, performing this test uncovers where we have a particular weakness in one material of a system of maybe 2 or 3 different insulators. Now this test allows the acid to be charged for 30 seconds, and then we remove the high voltage, and then we allow it to decay. And there's two types of current, again, that we will see. We will see the capacitance decay very quickly. Once that capacitance is decayed, we're now into the absorption, or the reabsorption, if you like. As it's discharging, there will be a current in decline, and we measure that after 1 minute. From that information, we have the current flowing after 60 seconds, which we measure in nanoamps, and we divide that by the multiple of the voltage and the capacitance of the insulation system in microfarads. And from that, we get a DD value, a dielectric discharge value. This time, we're actually looking for a low value. Okay, so we're looking for values under 2 as being a good quality insulator. Anything below that, between 2 and 4 is questionable, and anything below 4 is time to start thinking about moving and changing an asset out of service. Okay, let's move into the step voltage test. This is a time test. It's totally automatic, as all our diagnostic tests are. And this way in which it does it, we step up the voltage in ramps of, let's say, for example, there were 500 volts or 1000 volts at a time. And we will allow the IR value to charge the additional capacitance at the voltage. And then we will take a measurement at the end of a 30-second interval. It's very useful for carrying out predictive maintenance on motors that stop and start often. So they get exposed to greater starting currents and voltages. So the step test is very good for them. So when we perform a step test, here you can see the top line. It's done with a test at 500 volts, and you can see the shape of that. So the megohms is increasing with time. And again, if we did that at 2.5 kV, this will show an insulation weakness because it's actually beginning to drop off. In the 500 volts, it's continuing to climb, but in the 2.5 kV, you can see the IR value beginning to drop, which shows an insulation weakness. So when we perform the step test, here we can see the steps. Again, there's 500 volts per step. And at the end of the first 60 seconds, once you've done the initial 500 volt step, we then take a value. We then measure the leakage current. This time we're looking more at the current as opposed to an IR value. And we can perform the same step again, another 500 volts for a duration of 60 seconds. At the end of that 60 seconds, we take another IR value, and we continue this on right up until the top of our voltage. In this case, is 2 kV. But this could be anything up to 15 kV with our S1 1568 tester. So, as you can see, on the lower red line, we're seeing more or less of a straight line, which indicates we have stable insulation. We can also see on the other red line, the middle line in between the blue and the stable insulation line, we can see because of the current is increasing quite dramatically, this indicates that there's an instability in the ground wall of the insulation. Okay, the ramp test is similar in some ways to the step voltage test, but instead of using five or more large jumps in the test voltage, the test voltage is ramped up in smaller steps and is arguably a more efficient way of assessing the condition of the insulation. The test techniques also allows the user to have more control and a slower and more continuous increase in the applied voltage. This is less likely to cause damage to insulation than the step voltage test. What we would see within the step voltage test, if we started to see a current going up very, very quickly, we could stop the test because we know that there's going to be an issue. We can also perform this. We can also stop the test with with a ramp test as well, because we're likely to see an increase in the current, a very rapid increase if there's a problem. So It's doing about 1 kV per minute as opposed to 1 kV per second, as we saw in the step voltage test. So the ramp test is a more refined and controllable step voltage test, which uses smaller increments of voltage or many more steps in a way. The leakage current is graphed continuously against the voltage rise, and the small defects in insulation can be accurately detected. So equipment close to failure can be tested without risking damage. The ramp test, which is defined by IEEE 952.002, indicates the output for good insulation can be expected to be linear. But if the current seems to rise quickly, it's an indication the insulation is beginning to fail, and then the test can be stopped quickly. Now here you can see there's some traces, different materials work in different ways. These have different test currents as the voltage is ramped up. And these are typical graphs for good quality insulation materials. In this one, we can see a number of different shapes to these ramp tests. On the left, we can see where the current starts to go up quite rapidly. This indicates there's moisture ingress and possibly into the cable. On the middle one, we're seeing some localized weakness. Yeah, there's been a quick dramatic rise in the current, a sharp acceleration in the current rate. And again, that indicates a localized weakness. And on the right-hand side, we can see a very stable current, and then it starts to do all sorts of things and goes up again. So this indicates cracked insulation. So any sudden increase in current usually indicates an imminent breakdown. We can also use the ramp test to compare phases. So here on the left-hand side, we can see two phases, phase A and phase B, and their graph is quite similar. But when we do the same test with the same voltage rise rate, we can see that obviously the current is going up much more dramatically. So that indicates there's so the C phase has actually got an issue. So if it was all three the same, we'd know that was good, or all degrading at the same time. But here we can see that the C phase is actually degrading at a worse rate. So this test has revealed an issue with one of the phases. On the right-hand side, again, we're now looking at the megohm value on the left-hand axis, and also we can see that the voltage is rising on the bottom axis. So as you can see in the red one, we see a decreasing insulation resistant value as we apply an increase in voltage. This indicates a poor insulation. There's something obviously untoward with that one. However, at the top line, we can see a constant IR value irrespective of the voltage that we're testing at, and this indicates a good insulation resistor. So, every part of the electrical power infrastructure, from the point of generation through transmission and distribution to eventual use by the consumer, relies on effective insulation. Continuing availability of the electricity network is of paramount importance, and insulation resistance values, or isolation testing as it's sometimes known in some regions, has become one of the most widely used and accepted methods to determine the quality of the insulation. So it's clearly essential when we measure insulation resistance values that we must be able to fully rely upon the results that we obtain. Now, when we make an insulation resistance test, a known high DC voltage is applied to the asset under test, and the resulting current flow is measured. In some cases, we're measuring nanoamps, very, very small amps. So this is using Ohm's law, simple Ohm's law, to convert it into an insulation resistance value. Now, comparing this insulation resistance value with predetermined pass-fail criteria helps us in determining the safety and the quality of the asset's insulation system. However, we need to eliminate as many variables as we can and focus only on what really matters, the true insulation resistance measurement, or IR value, of the underlying insulation material. So, it's an important decisions are made on an asset's life cycle There's implications for infrastructure investment. There's the availability of the network to consider. And obviously, you've got to effectively plan the maintenance activities. This is all dependent upon the availability of reliable, accurate insulation resistance data. So to do that, we need to eliminate the variables that can affect the values. So some of the variables that affect the IR value are shown here. Most of these variables we have little control over. In many cases, we may be testing outside, exposed to elements, and although we don't advocate testing in the rain, sometimes you may need to do so. We may encounter different temperatures, changes in humidity. There could be solar effects as clouds appear and disappear above our assets under test. There could be fluctuating wind speeds and ever-changing wind direction. And of course, surface leakage effects caused by contamination. So assets under test are exposed to some degree or other to at least some of these effects every time we test. These are physical and environmental conditions over which we have little or no control over their presence. But there is an answer, and we simply have to deal with them by eliminating their effects on the insulation tester and the corresponding values that it measures. Now, we already know that as temperature increases, this presents an adverse effect on the insulation resistance values. As a general rule of thumb, an asset's insulation temperature if it rises by 10 degrees centigrade, its IR value may reduce by as much as 50%. So as we use assets at greater and greater temperatures, for example, as an electric motor, its IR value may fall quite dramatically. Take an example of a Class F motor, which is rated to 155 degrees C. The allowable temperature rise for the motor's winding insulation may range from 105 to 115 degrees C above ambient, and the ambient they usually regard as 40 degrees C. So this can reduce a typical IR value from, let's say it's 5 gigohm ambient, but it can reduce to just 40 megohms at 150 degrees C. So it's very important that we consider temperature. Now, the way in which we can do that, there's little that can be done to combat the effect of temperature on IR value, but they actually can be compensated for or corrected either in software or on board within the instrument using temperature correction. Now, the new Mega MTR 105 rotating machinery tester is an example of an instrument with onboard temperature compensation for its IR test. Let's move on to the other factors such as humidity, moisture, solar wind. But first, a little bit of background. In assets such as coil windings found in motors or on HV bushings, the surface of the insulation presents quite a large area on which contamination can land and build. Contamination can occur naturally due to airborne pollutants such as dust. It could be salt from the air in a salty environment where we are here in Dover. We're very close to the sea. It could be diesel particulates from vehicles. These all add up to contaminate the surface of an asset. Animal feces in the form of bird droppings can also contaminate an asset, such as on the HV bushings mentioned earlier. Motor windings are often contaminated with oil from bearings or from dust drawn in by the motor's cooling fan. There's all these things that we need to try and avoid effect on the IR values that we measure. So all these surface effects, all these environmental effects that we just talked about, the contamination affects the surface of the insulator. It presents a low resistance path for a surface leakage current to flow over the surface of the asset. Here we use the HV bushing as an example. So the surface leakage current is in addition to the leakage current or conduction current that we see that goes through the insulation material. In this diagram we see a typical HV bushing. There's contamination on the surface of the fins, providing a low resistance path for the surface leakage current to flow. We can see the surface leakage current shown in brown. The leakage current through the insulator is shown in blue. These two currents combine at the top of the bushing, and these two currents combine flow into the negative or the low potential side of the terminal of the instrument where the measurement takes place, where the magic takes place, if you like to call it. Now, the environmental effects of humidity, moisture, solar, wind all affect the value of the current that flows over the surface of the material. The greater the contamination, the greater the surface leakage current. And as the contamination layer on the surface of the acid attracts increased moisture content from humid air, the surface leakage current also increases. So as the sun comes out from behind the cloud or the wind speed increases, the moisture contained in the contaminated layer may evaporate off, and we begin to see better values of IR because of reduced surface leakage current. With fluctuating sun, wind speeds and humidity levels, the surface leakage current is forever changing and is never predictable. So as a result of contamination, we are presented with not one but two current paths, one through the insulation material and one over the surface of the insulation material. The IR value displayed will, as a result, always be lower than expected. This may cause the acid to be incorrectly condemned to the recycling bin and the unnecessary expense of an acid replacement. So how can we hope to eliminate these effects? Fortunately, there is an answer, and that is the guard terminal. So when we make an insulation test, we're often so preoccupied with the resistance of the actual insulator that we forget about the resistance path on the outer surface of the insulation material. This surface leakage path can be very much part of what we measure, and as we've shown, it could dramatically affect the results, sometimes with far-reaching consequences. The guard terminal provides us with a method to remove the effect of surface leakage on our measurements and arrive at true IR values. We can also use the guard terminal to perform a very simple diagnostic test. If we perform two very simple IR tests, one without the guard terminal and the second with the guard terminal being utilised, a quick comparison of the results can clearly show how any contamination of the insulation system, be it motor windings covered in dust or oil, or a HV bushing covered in general grime and dirt. So the guard terminal can be seen as the very first IR diagnostic test, and it can complement other tests such as PI and DAR. By using this very first diagnostic test, we can readily determine if the acid's insulation is really producing a low IR value, that it's actually degraded, or if it's just contaminated. If it's just contaminated, we can simply schedule a cleaning operation and restore the acid's IR value to safer levels. Now, the guard terminal is a very underused and undervalued method, but when we're using trending, it actually removes as many variables as we can. If we add the temperature compensation in, then we've got rid of everything that can affect the reading. We've got true IR values. Now, from that, we can determine the quality of the insulation, and we can also obviously make sure that our acid is safe. So once we've removed the effect of any surface contamination and our environmental effects from our IR test, using the guard terminal, we can now get down to the true IR values, values that we can rely upon, values that we have complete conviction in, values that we can use to determine the future of an asset. We can make sensible decisions based upon the information that we've got. Now, in addition to the IR tests, if we perform DAR tests, the dielectric discharge test, or the polarization index test, the step voltage and the ramp, as we perform more and more of these tests, we get a more and more holistic view of the insulation material's quality. So here we can see on the right hand side, we can see some, I believe this is Costa Rican divers. They're creating an artificial reef out of failed HV bushings. So they fail these bushings, they put them on this metal spigot, and they create a new lease of life for these HV bushings. But quite frankly, how many of these bushings was actually just in need of a clean and hadn't really failed, they just needed a clean? We will never know. So when we carry out insulation resistance testing and we note low test results, before we condemn the acid to the bin, there is one factor that is often forgotten, and that is the surface leakage due to contamination or dirt. So as I mentioned earlier, if we perform a simple test with and without the guard terminal employed, we're able to determine if it's actually the material that's damaged it's degraded or that it needs cleaning. So, you know, the surface leakage needs to be eliminated from the reading. That is where the guard terminal comes into play. Remember, if there's a high or a compliant reading, there is no need to use the guard terminal. So if you've got a reading that's in excess of the value that it should be for the insulation, as advised by the manufacturer, you might not need to use the guard terminal. But if you're trending, then you should use it each and every time. So with a contaminated acid, the IR value will be measured as a result will always be lower than we expect. So here we can see in the diagram, we see the contamination manifests itself and lowers the IR value that is measured. So using a resistor to represent a typical expected IR value of 600 megohms, with a contamination being represented by two 3 megohm resistors in parallel with the 600 megohm resistor. Using the formula for resistors in parallel, we can see how the surface contamination quickly reduces an expected value of 600 megohms to a value just under 3 megohms. So this destroyed the result that we were expecting. This just shows how dramatic an effect that surface leakage can have on our IR values. So in this instance, we'd probably be condemning this acid because it's got such a low IR value. So regarding the guard terminal, with the addition of a third wire to the insulation resistance test, instead of doing a 2-wire test, we're now doing a 3-wire test. We're able to wrap a conductive wire or conductive rubber around the bushing, using the bushing as an example again, and this provides a path for the surface leakage current to be diverted away from the measurement circuit contained within the negative terminal. So this leaves us with only the leakage current through the insulation material is being considered and being measured. And this provides us with the true, accurate IR value that we're looking for, that we can confidently rely upon. It's a value that we can base sound decisions upon in the next chapter of this acid's life. In this diagram, we can see the black conductive wrapper wrapped around the bushing. This is in turn connected to the royal blue test lead and is diverted away to the guard terminal, which is the third terminal on the IR tester. So putting temperature to one side for a moment, the guard terminal can eliminate all those environmental factors we mentioned earlier. Factors such as humidity, moisture, wind and solar are simply swept aside with the use of the guard terminal and suitable connections to the asset. We also have, where we have multiple insulators and multiple leakage paths, we have a kit where we can link up all these assets together and take them back to the guard terminal, so we can remove all surface leakage effects and eliminate them from our measurements. Now, although we're using a HV bushing as our example asset, the guard terminal can be employed on many other assets to eliminate these factors. Transformers are typical. We can guard out the different tap-ins, also different windings that we're not testing at that point in time. We can guard them out. Motors, we can guard them out, and also cables. There's just a few examples of where we can use the guard terminal. So if you can identify a surface leakage path or paths, then they can be guarded out, and the result IR value measured can be fully relied upon. So onto the guard terminal challenge. Okay, so first of all, when designing an insulation resistance tester, we're required to meet a number of very stringent international standards and safety requirements. To add to this, Mega's own safety standards often place additional pressure on safety considerations. To be quite frank, we're very hot on safety, and we don't compromise on that ever. Our S1 range of high-performance diagnostic insulation resistance testers are rated to Cat 4 600 volts, which mean they must protect both the instrument and the user from up to 8 kV transient over voltages. The IEC 61010 standard provides us with insulation methods, distances for creepage and clearance, and some suggested components to limit its over voltage. But when it comes to the instrument, we also need to protect the terminals. Now, sorry, just going to go back very slightly. So a way in which this can be done, we need to protect the instrument and the user from these transients. We need to employ some technology within our terminals to ensure that anything's not transmitted to the instrument or transmitted to the user that could be pressing a button or turning a knob at the time of that transient. The second challenge to overcome is accuracy. One way in which a competitor has found a way of getting their instrument to have some Cat 4 protection or additional EMC protection is they've used a 1,000 ohm resistor at the guard terminal to limit the voltage and current that the instrument might see in the event of a transient, that energy, limit that energy. But here we can see on the bottom right hand side, we can see the calculations, and we've actually got a reading of 900 megohms, which should be 1,000 megohms. So we've got about an 11% error on this measurement, and this is caused primarily by the 1,000 ohm resistor that they've put to try and improve their Cat rating. So the use of resistors is not a good idea. However, many competitors revert to this method. Mega doesn't do this. Mega has very fast changing circuits that could detect a transient and block it. And when the transient's decayed, that blocking is then lifted. Now the advantage of that is there's no impact on the accuracy of the instrument. We don't worsen the accuracy of the instrument by putting resistors in there. We keep the impedance of our circuit low when we measure, and then we increase the impedance of our circuit when a transient is detected. So here we need to talk about the test voltage. Now, safety is not the only criteria, but we need to think about the test voltage. Now, if we operate in this way, we can see that we've got a 2.5 megohm load across between the guard terminal and the positive. So we've got, if we divide the test current, in this case it's 500 volts, divided by the 2.5 megohm, we get a 2 milliamp requirement for our test current. Now, the instrument we're concerned with today is the S1, and the S1 has 6 milliamps of short circuit current, so it can easily supply the 2 milliamps required by this particular resistance value. And as a result, the test voltage won't collapse. If we have an instrument that's only got a 1 milliamp output, then the test voltage would collapse. It wouldn't be able to support the test voltage, and this would negate any tests that you're performing. If you can't keep the test voltage at the selected level, then the test is effectively null and void. So, to summarise the way in which we design these guard terminals, we need to consider the Cat safety rating. We need to consider the guard terminal performance, i.e. the accuracy of the instrument. We need to consider the test voltage and maintaining that. And there's also cost implications, and the way in which we design the guard terminal also comes into play. Now, it's quite inexpensive to add resistors to the guard terminal and the other terminals for that matter, but it's not the best way, as we've seen earlier. The way in which Mega does it adds a little bit more cost to the way in which we design it. However, we include that as standard on most of our testers that have the guard terminal. So the challenge is to control costs, maintain safety, and we've done this, and we've been able to deliver exceptional guard terminal performance. So what do we need to look out for when we're thinking about buying an IR tester? Well, first of all, we need to look at the way in which the protection is given to us as users of the instrument. What level is that Cat rating? Is it Cat 3 or a Cat 4 environment? How about its EMC, electromagnetic compatibility protection? And how much it can withstand without impairing or impacting the instrument? Can it sustain the test voltage that we need? Yeah. is it got enough current to be able to drive them resistances? Now, most guard terminals fail to perform well, so you have to be very careful when selecting. We mentioned earlier we had accuracy concerns. You know, is it going to affect the accuracy? Some manufacturers quote their performance of their guard terminal atypical test voltages. So it could be that it's you know, you've got buying a 5 or 10 or 15 kV IR tester, but the performance of the guard terminal is quoted down at 50 volts, which is atypical and unlikely that you'll use that value for a test voltage. Some of this information is hidden in the small print. You know, the manuals is the legal document in which you can determine the quality of an instrument. Now, also, some people only rate the cat rate the guard terminal. So make sure that all terminals that you have on your instrument are cat rated. So moving on a little bit more further, there's some further reading for you with regard to the guard terminal. We've published many explanations about the guard terminal. These two stand out as some of the best, and I believe that we will be sending these out to you at the end of the webinar for your further bedtime reading. Okay, let's get on to some of the products that Mega manufacture. Here we can see a range of products. They've all got the guard terminal on them. We start on the bottom left. We've got a 1000 volt tester. Sorry, it's a 2.5 kV handheld tester. This is an IR tester. It's a very, very beautiful instrument, and actually, it's the performance of its guard terminal is as good as all of our products. We don't differentiate. We use the same technology across the full range of products. Then we move up to the top right-hand corner, one of our most recent additions to the Mega stable. We have the MTR 105, which again is a handheld tester to 1000 volts, and this is primarily aimed at AC induction motor testing, but also other rotating machinery, again equipped with the guard terminal. And then we have the S1. The S1 is available in 5, 10 and 15 kV outputs. Our 15 kV output provides you with the ability to test up to 35 teraohms in a portable unit. Look at the S1s in a little bit more detail. So when you see the code of the instrument, the 568, 1068, 1568, the initial value, the 5, the 10 or the 15, refers to the maximum output voltage, i.e. 5 kV, 10 kV or 15 kV respectively. The 6 refers to the 6 milliamps of short circuit or charging current offered by the Series 1 range. And the 8 refers to the 8 milliamps of noise rejection capability offered again by the Series 1 range. Now this high noise immunity is provided by both the hardware and the averaging filters, which has 4 settings. It comes with a compact, rugged case, which is actually a dual case construction. The inner case is a clear fire retardant case. However, once you start adding fire retardant materials to some polymers, they tend to get brittle. So we've added a tough, rugged outer case to withstand the rigors of field testing wherever you go. This has the added advantage that we're able to contain the electronics within the inner case, enabling you to very quickly, with the use of a screwdriver, change your battery without impacting on any other calibration constants within the instrument. We've also got the capability to record relative humidity and temperature. We've got a very fast charging time of up just 2 hours, and also you can use it on a mains. And we've got USB remote control, and we can download data either using Bluetooth or USB. Now, the main key features of the S1 range are the higher noise immunity and the charging current. That is what really puts it above many of our competitors. So we're able to charge that capacitance in the cable very quickly, which means you're able to go on. I'm using cable as the example, but in most cases, anywhere you've got high capacitive load, then we can charge it much more quickly using the S1 due to its 6 milliamps of short circuit current. So there you are. You have the S1 high performance range. And if you do need to get in contact for further information, please use the contact information here. And I thank you for listening. I think Michael will now take over.
Hello, everyone. Can you hear me, Grace?
Yes, I can hear you, Michael.
All right. So yeah, sorry about that. Okay, so guys, let's move on now to the question and answer portion. So for those who are leaving, by the way, please be reminded that don't forget to answer the survey that will pop up on your screen, because that will really help us a lot in improving our future webinars. All right. So now let's go on with the question number one. From Nito. What's this? When testing in high interference area, should we directly turn on the filter or just run the test when turn on the filter afterwards? Will it be safe for the instrument? Is there any recommended test voltage to start with? For example, while testing 150 or 20 kV transformer, can we test directly at 5 or 10 kV? Okay. So I will try to answer one by one. So the first question is, when testing in high interference area, should we directly turn on the filter or just run the test when turn on the filter afterwards? Well, when you know that it is a high interference area, for me, I prefer to turn on immediately, because when the filter is on, the test will take some time. It will be a longer test time, because for example, if you are using S1, then you have actually the option of 10 seconds, 20 seconds to 100 seconds. So, and the S1 is doing series of tests and then do the averaging. So that is how the filter works. So if you know that it's really a high interference area, I suggest to turn it on right away, because if you do the first test without any filter, then you might end up doing a test again, because because that is inaccurate already. You will have a result which is inaccurate. So I prefer to turn it on. For the case that the area is, that there is no so much interference, then I would prefer the filter to be off, just to speed up the test. Okay, so it will be faster if the filter is off. And or you can on the filter and select the 10 seconds. So if you're doing a spot test, then just do the 10 seconds filter, and that will be okay. That will be a fast test anyway. Will it be safe for the instrument? Is there any? Yeah, it will be safe for the instrument. Is there any recommended test voltage to start? Well, by the way, when it comes to test voltage, we have a recommended test voltage from NETA. If I can show you the screen. Can you see my screen? So this is the table from the NETA standard, which you can see here a different nominal rating in voltage and volts of the equipment under test. And this is the minimum test voltage you should inject. So for example, you have here a 34.5 kV and above, then you must use 15 kV. And the test result that you should have in order to pass is 100,000 mega ohm. Okay. So for the nominal rating of 5 kV, for example, then the minimum test voltage should be at least 2,500, and the recommended minimum insulation resistance should be 1,000 mega ohm. But to be safe, just don't exceed the limit of the nominal rated, or the rated nominal voltage. Okay, because if you injected, a higher voltage than the nominal, then you can hear some sound, and you might destroy, or you might damage the insulation. Okay. Another question here. Another question here. Do we have to clean the surface before the test? Yeah, it was mentioned in the presentation that the surface leakage can affect the result. That's why you need to guard to eliminate that surface leakage. But if you clean the surface before the test, then it could probably give you a better results in the first place without any using the guard. But still, it is recommended to use the guard. So if you clean the surface, then it will minimize the problem. What is the pass-fail criteria? So as you can see here in the table, this is according to the NEMA or NETA standard, sorry, table 100.1. So see here, this is the recommended minimum. So everything below will be failed. Yeah, will be the assessment for fail. So another question here. Have you read this one, Zoom? Can insulation resistance tester substitute the conventional high-path test set if we want to test a short span of cable which required test voltage of 15 kV DC as the insulation tester can produce 15 kV DC too? Zoom, can you answer this one or?
Okay, Michael. So in my understanding, they want to test cable using our 15 kV insulation resistance test. Yeah. In theoretical, actually, it will be the same method. We produce the DC output to the cable, but the expected result it will be different because our insulation resistance test will provide you mega ohm value, and when you use the hypo test, the expected result is in milliamp or microamp. The result will be in current, not in the mega ohm. So as long as the capacity of our instrument enough to test the cable, you still can use it for testing the cable. But if the capacitance is too high, I'm not sure it can be done with our insulation resistance test. Yeah, but principally it will be the same. Yeah. Yes, Michael.
Okay, yeah, that's correct, bro. It will depends on the limitation of the test equipment as well. So high path is much higher or much powerful than the insulation tester. So the good thing with, because when you do the high path, you are measuring the leakage current. That's why it is displaying the leakage current. When you do the insulation testing, you are measuring the resistance there. And so it will display the resistance value of the insulation. But of course, it will also display the leakage current. But with the limitation, of course, how much power that our DC insulation tester can do, that will be the limitation for the leakage currents measured. Okay. But remember, when we do the high path, we might damage the cable if it is already have some damage. So for example, it has a small hole inside, and you try to use the high path, expect that that hole will become bigger, right? Because we are doing the high path, so we are stressing the the insulation of the cable. While when we do the DC insulation, so we are just checking the resistance, how much resistance we can have. Another question. I mean, do we need to use the guard? Yes, sir. For better accuracy then you can have the you must do the guard. what is the best thing to do of if while conducting insulation test you see the reading jumping or not stable? So that could be you have a high capacitance in there, sir, which is the capacitance is being charging and then discharge again. So that's why you have a very unstable reading. So I would suggest to do time for that. If you do the DAR and polarization index test for those kind of situation. So when we perform IR or PI test on power transformer that have different voltage levels, such as high voltage bushing and neutral bushing, do you recommend use need to guard or terminal or just only neutral bushing? So the good thing with the guard terminal, sir, is it will eliminate any resistance that should not be included in the measurement. So put the terminal or guard terminal, put that into the terminal that is not being tested, so that any leakage current that will flow on that terminal will not be considered in the computation. I mean, it will not add up into the computation. So you will have a better accuracy in doing the testing. Okay. Correct me to, high path is okay for short period because it's really destructive test for me. Do we have to connect the guard lead to the surface of the bushing? Yes, sir. You have to connect the guard for better accuracy. What kind of clamp do I have to use to connect the guard to the insulators? The one included with our equipment, sir, we already have the clamp in there. It's the same as the high voltage clamps that we have. So, yeah. All right, so I guess that's all the questions that we have for now, guys. So I just want to say thank you, everyone, for attending this webinar and for joining us today. And for any of you who have any more questions, please send us an email and we'll try to answer it back. So again, thank you so much for attending this webinar and hope to see you again next time. Thank you so much, everyone, and goodbye. Please stay safe.